Let's take a quick look at complex impedances. The basic building blocks of most of our passive circuits are the resistor, the capacitor, and the inductor, which are shown here, along with their key equations. For the resistor, it's V equals IR. That relates the current to the voltage. In the case of the capacitor, it's I equals C dV dt. That relates current to voltage. And for the inductor, it's V equals L di dt, which again relates current to voltage. So these are all time-based equations. What I'd like to do now is take the Fourier transform of all three of these to get a frequency-based equation. So in the case of the resistor, it's voltage as a function of frequency equals current as a function of frequency times resistance. In the case of the capacitor, it's current as a function of frequency equals capacitance as a function of frequency. Sorry, capacitance is not a function of frequency, it's a constant. So it's capacitance times the derivative of voltage, which is j omega times voltage as a function of frequency. And in the case of the inductor, it's voltage equals inductance times the derivative of the current. And then finally, I'm going to rewrite these just a little bit. The resistance one won't change. It's still going to be V equals IR. For the capacitor, it's going to be V equals I times 1 over j omega c. And in the case of the inductor, it's going to be V equals I times j omega L. So what you can see now is that we have a pattern. In all three cases, when we take the Fourier transform, when we start to think about this from a frequency perspective, what we have is V equals IR, except that the R can now be complex. It can contain both magnitude and phase, and it can be frequency dependent. And this is what we call impedance. Impedance is pretty cool because it's going to allow us to massively simplify our circuit analysis. So impedance we can sort of think of as complex resistance, which means it's resistance that has magnitude and phase, and in many cases can also be frequency dependent, right? So for example, in the case of a capacitor, the higher the frequency, the lower the impedance. Okay, so a capacitor starts to act like a short at high frequencies. Let's discuss that very briefly. Because the capacitor is the equation is the way it is, for the capacitor, as the frequency goes up, the impedance Z goes down. Okay, which means that at very high frequencies, the impedance gets so low that the cap shorts. So at high frequencies, the cap shorts, which is what it means to have a low impedance. And conversely, at low frequencies, the impedance gets higher, and when the frequency goes to 0, the cap has such a high impedance that we can think of it as an open circuit. Conversely, the inductor has the property that as frequency goes up, its impedance goes up. So it sort of works in opposite to the capacitor. So in other words, at high frequencies, it has a very high impedance, which means it acts like an open at very high frequencies. And at low frequencies, its impedance gets really, really small, and the smallest of all impedance is a short. Okay, it shorts at low frequencies. So that is a handy way to think about our circuit elements. Now, look how helpful this can make analysis. Let's go ahead and redraw our RC filter from before. So resistor, capacitor. And now, instead of even bothering to write the differential equation that governs this circuit, I'm just going to do an impedance analysis. I'm going to say that this resistor has an impedance of R. I'm going to say that this capacitor has an impedance of 1 over j omega c. And then I can say that the output voltage can be defined using voltage divider. And the way voltage divider works is it's the output resistor, in this case the output impedance of 1 over j omega c, divided by the sum of the impedances, R plus 1 over j omega c. And if we multiply numerator and denominator by 1 over j omega c, we get 1 over j omega rc plus 1, which is the same transfer function that we had all along. Okay, that's the same transfer function we worked out in the previous video. Now look how handy this is. You can now get the transfer function for just about any circuit, right? What if I come along now and I give you a resistor, a capacitor, and let's say another resistor? Finding and solving the differential equation for this thing is a bit of a bear, but if you do it using impedances, it's not that bad. R1, C, R2. Let's assume that the output voltage is over here at the right. That's sort of our standard notation. So this will be V out. This will be V in. And now our output voltage can be expressed simply as R2 in parallel with 1 over j omega c all over R1 plus R2 in parallel with 1 over j omega c. And then we can work out in the margin that the parallel impedance of R2 and C it's always product over sum. So the parallel impedance, R2 parallel 1 over j omega c, is going to equal product over sum which I can then simplify as, if I multiply through numerator and denominator by j omega c, I get R2 over j omega R2c plus 1. And then that expression I can substitute in now for both of these terms, which is going to be a little bit ugly, but I think if I do my math right, let's see, I don't think I can do this without an intermediate step. So again, the numerator is going to be R2 over j omega R2 c plus 1 all over R1 plus R2 over j omega R2c plus 1. And that is ugly, so I'm going to multiply numerator and denominator by j omega R2c plus 1. And that's going to give me R2 over, let's see, it's going to be j omega R1 R2 c plus R1 plus R2. Okay, and that is the transfer function of this circuit. Now, does this make sense? We can do a logical analysis. At super low frequencies, that capacitor is going to be an open. And if that capacitor is an open, then all I'm left with is the voltage divider, R2 over R1 plus R2. Does the equation predict that? Well, at super low frequencies, omega will go to 0, and I'm left with R2 over R1 plus R2, which is good. That matches intuition. Now, at super high frequencies, that capacitor is going to short. If that capacitor is going to short, then it doesn't matter what R1 and R2 are doing. V out will be just shorted to ground. So, does our equation predict that for very high frequencies, our output is 0? And the answer is yes. If omega becomes infinity, then it doesn't matter what my numerator is or the other terms in the denominator, my output is going to be 0. Alright, so, sorry, I just forgot to mark that there's a times V in on all of these. Okay, times V in, just to be accurate. Good. So this is how we can use impedances to make circuit analysis much easier and even do away with the much feared differential equation.